Hello everyone. Welcome to the SWAYAM NPTEL course on Mathematical Geophysics. This is continuation of the module number 6, Wave Dynamics in Geophysics. This is the lecture number 5 of this module, Internal Gravity Waves. In this lecture, the concepts covered are related to the internal gravity waves. First, we will look into the concept of the internal gravity wave. Then we will derive the internal gravity wave equation. Then we will look at the dispersion relation which governs the characteristics of the propagation of internal gravity waves. Finally, we will be looking into various geophysical applications which utilize internal gravity wave phenomena. So let us begin. First, what is an internal gravity wave? Now, internal gravity waves are oscillations which occur within a fluid medium. This fluid medium can be either ocean or atmosphere, or it can also be the liquid iron of the Earth's outer core. In the internal gravity wave, the restoring force is the force of gravity. Just like we had the Coriolis force acting as restoring force for inertial waves. Now, these are dependent upon the gravity as the restoring force, thus it is called an internal gravity wave. Internal because these waves occur within the fluid rather than on the surface of the fluid. The surface waves are different from the internal gravity wave. Now, two forces are important in internal gravity waves. First is the buoyancy force, which is coming from the gravity, and stratification, which can be thermal or chemical composition. Now, these buoyancy force interact with inertial forces of the fluid and generate the internal gravity wave. The inertial forces are coming due to the acceleration of the fluid and its mass, while buoyancy forces are generated due to stratification. Thus, stratified fluids are a necessary ingredient for internal gravity waves. Now, we will understand what is meant by stratification. Stratification means the density varies with depth, such as thermoclines in oceans. In oceans, at various depths, the density of the water is different. Similarly, in the atmosphere also, the density of the air is different at different heights. Like in troposphere of the atmosphere, in the first 10 kilometers from the surface of the earth, the density of the air changes. Such change in the density of the medium, which is fluid, leads to stratification, and this is useful to generate buoyancy forces which governs the production of internal gravity wave. Now look at this diagram here. This diagram shows the formation of internal waves at the interface of two density layers. These are the two density layers. Below we have high density layer and above there is a low density layer. As we know, low density layer lying on top of high density layer forms a stable interface, which means that these immiscible fluids will not mix and there will be no upside down motion. Thus, the high density layer will be always below the low density layer. Now, if we perturb the interface of these layers, it will generate a wave. These waves are a type of internal gravity waves which are occurring within the fluid domain. These are not the same as the surface waves which are occurring at the top of the liquid. In this adjacent diagram, we can see the configuration of the system is such that we have one cold boundary at the bottom and hot boundary at the top. On both sides, we have insulating boundaries. Now gravity is pointing downwards. In this diagram, and the setting is such that cold boundary at the bottom would lead to high density of the medium. Here density is denoted by rho. Now, due to the low density being above the high density material, this system is a stable system. This can give rise to internal gravity waves within the fluid if perturbed. So we can see that if there is a perturbation such as this one, where we have alternating layers of fluid motion such that each layer is of a different temperature with alternating hot and cold fluids moving in opposite directions. This leads to an internal gravity wave. One can also see that the phase velocity is perpendicular to the group velocity. The phase velocity is the direction where the crests and troughs of the wave lies. Now we can see that the crests, which are hot fluids, and the troughs, which are cold fluids, they are aligned in the direction of fluid velocity. This is the direction where crest and troughs follow one another. However, the fluid motion is perpendicular. The fluid transfers energy and hence information across in the perpendicular direction to the phase velocity. Thus, the group velocity is in the direction of the propagation of information. These are the few typical illustrations of internal gravity waves. Now we will look into the rigorous mathematical details of internal gravity wave and the generation and the dispersion relation which gives their characteristics. The internal gravity wave equation. Now, to obtain the equation which governs the generation and propagation of internal gravity waves, we have to consider the Newton's Reynolds decomposition. The Reynolds decomposition is given as follows. Here P is pressure, rho is density, U vector is the velocity field, T is the temperature. The star denotes steady time independent factor. Thus, any quantity such as pressure or temperature can be decomposed into its background state, which is steady, and the perturbation state, which is unsteady. The background state is denoted by star. And the perturbation state is denoted by prime. Thus, We can say that the background state is a function of space only, while the perturbation state P prime is function of both space and time. Let us consider the xz plane in a Cartesian coordinate system. In the xz plane, which is also equivalent to y equals to constant, we have a continuous, stratified and unbounded fluid. Let's say we are looking at the y equal to 0 plane in x and z direction as shown here. The fluid is unbounded, which means there are no boundaries. Then we can look at the linearized diffusionless perturbation state governing equations. These equations can be obtained from the Newton's laws of motion for fluids. We have looked into such equations previously in the formulation of inertial wave dynamics. We will also look into the heat transfer equation. These are the three equations. The first equation, divergence of u equals 0. If the divergence of any quantity equals 0, it means that there is no input or output from the region under consideration, which means the conservation of mass. Note that these equations are written per unit mass. Hence, mass does not appear in both sides of this equation. The second equation is the Newton's laws of motion, where if we multiply m on both sides, we'll have mass into acceleration equals net force. If we remove mass from both sides, we have acceleration equals force per unit mass. Thus, the left hand side is acceleration, which is given by del u by del t, equals the right hand side, which is force per unit mass, which is first term given by pressure gradient. The second term is the buoyancy force. The pressure gradient forces can apply mechanical forcing for the fluid motion, while buoyancy forcing can induce convective flows for the fluid. Now the third equation is the heat transfer equation. The first term is the evolution of temperature. The evolution of the temperature with time is being affected by the advection of temperature by the flow field. The advection of temperature is just the motion of a fluid parcel which has a particular temperature along the flow field. For example, if we have a particle like this of a certain temperature and the velocity field given by these arrows, then this particle will be moving in a path as shown by the dotted line. Now, as this parcel moves along this path, the temperature at various other regions will be changing because of the influx and outflux of the temperature. Thus, the temperature at any point, such as this cross mark, will be enhanced or diminished based on the passage of this fluid parcel, which may have a certain high temperature. So as this parcel crosses the crossing point, the temperature will rise and then it may fall. That would be detected by the evolution of temperature term here. Thus, we are tracking the evolution of temperature and the velocity field through these set of equations. So we are tracking the evolution of u and t using these three set of equations. Now, in the stratified region, the density is assumed to vary only in the vertical direction. Thus, the temperature variation can be considered only in the vertical direction. Therefore, we have the thermally stable region defined as del T by del Z positive and thermally unstable region defined as del T by del Z negative. This can be understood as let's say we have hot and cold regions like this with gravity pointing downwards. Now, hot regions will induce lower density while cold regions will induce higher density of the surrounding medium. Due to the condition that the low density is lying below the high density, the consequence can be the high density material taking the place of low density material. This overturning leads to instability. This unstable configuration can be now formulated like, considering this as the z axis, and T1 and T2 as the temperature of cold and hot regions respectively, we have now Z1 and Z2 are also representing the heights of cold and hot planes. We can see that as Z points upwards, Z1 is higher than Z2. While T1 is lower than T2 because T1 is colder temperature. Thus, the numerator is negative while the denominator is positive. This gives del T by del Z is negative, which is an unstable configuration. The opposite configuration can be obtained by reversing the hot and cold planes. This ensures that delta T becomes positive and del T by del Z becomes positive. This is a stable configuration because the density now becomes like this. Hot region will induce low density, cold regions will induce high density. This is a stable configuration because low density will not have the tendency to overturn high density. Thus, this Overturning is absent, making it a stable configuration. This is given by the thermally stable region del T by del Z positive. Now we look into the second term of the previous equation. Here, U dot grad T can be written as the dot product between the uz and dt dz, as there is no temperature variation along x and y axis. Since the temperature varies only along the axial direction, that is z. Thus, we have the heat transfer equation simplified to del T prime by del T equals uz prime del T star by del Z. Note that only T prime exists here, as del T star by del T goes to 0 because T star is independent of time. On the right hand side, we have uz prime multiplied by del T star by del Z with a minus sign. Now, for the equation number 2 as shown here, we are going to operate two operations that are given by these operators. The first operator is z dot curl. The second operator is the axial component of double curl of equation 2. We have seen in previous lectures how to evaluate the curl. After evaluating the curl on this vector equation number 2, on both sides, we've obtained this equation where xi is curl of u, which is the vorticity, and taking the z component, we have xi subscript z. This is the z component of the vorticity with prime as the perturbation quantity. The pressure gradient term vanishes due to curl because curl of gradient is always equals to 0. Thus, the third term, curl of alpha gt prime z, also does not have any z component. Since this equation is a z component equation, we do not have any component of the buoyancy term. Due to the operation of curl, the buoyancy term vanishes along the z-axis. Note that do not confuse between the buoyancy term along z and curl of buoyancy term along z. The buoyancy term exists along the z-axis, but the curl of the buoyancy term does not exist along the z-axis. Hence, the equation number 5 has 0 on the right hand side. Now, the second equation. This equation is obtained after taking double curl of the heat transfer equation. Double curl of velocity gives Laplacian of uz, and we have the z component of the double curl of buoyancy term given by alpha g Laplacian of t in the horizontal direction. The horizontal Laplacian is given by del x square, while the total Laplacian is del by del x square plus del by del y square. Now, operating del by del t on equation number 6 gives us second derivative of Laplacian uz with time equals alpha g horizontal Laplacian of del t prime by del t. This we have obtained such that we can eliminate del t prime by del t from equation 7 using equation 5. This we have performed because our aim is to eliminate del t prime by del t using previous equations. Thus, we substitute equation number 4 to eliminate del t prime by del t. This gives del square by del t square of Laplacian uz equals minus alpha g del t prime by del z Laplacian of uz prime. This is coming from this equation where we have substituted del t prime by del t here. Now, if we perform the further algebraic derivations, we obtain equation 9 substituted into equation 8 gives. Now, substituting equation 9 into 8, we have minus n square Laplacian of uz prime, where n square denotes the Brunt-Väisälä frequency. This can be written in operatorial form as the operator L is del by del t square Laplacian plus n square horizontal Laplacian of uz prime equals 0. Note that this is a wave equation. It has the components of wave equation such as the time derivative and the spatial derivatives as two terms for the velocity. This is the final form of the internal gravity wave equation. Now, the Brunt-Väisälä frequency, which we have introduced in equation 10, is defined as square root of alpha g del t prime by del z. We can understand that the Brunt-Väisälä frequency is dependent upon the thermal stratification del t prime by del z. Now coming to the dispersion relation. The dispersion relation gives the properties of internal gravity waves that can be determined by using normal mode analysis in similar lines as the inertial wave. This is the normal mode expansion for the velocity perturbation uz prime. We have uz prime equals to amplitude u naught exponential to the power I kx plus mz minus omega t. Here k and m are wave numbers along x and z directions respectively, while omega is the frequency. Having the normal mode analysis into space and time as waves, we substitute uz prime expression as obtained in equation number 3 into equation number 12, which is the internal gravity wave equation. Now we have the simplified form as omega square equals n square kh square by k square. The kh square is the horizontal wave number vector, which is nothing but k square. This is because the horizontal Laplacian is only in the direction of x, that is del square by del x square. This gives kh square equals k square, as k is the wave number along x. The total wave number vector k square is k square plus m square. Thus we have the frequency wave number relation given by this. This means that for waves having different wave numbers, the frequency of oscillation are different for internal gravity waves. Now we come to the various applications of the internal gravity waves in geophysics. First, we consider the atmospheric applications. Internal gravity waves transport energy and momentum in vertical and horizontal direction in atmosphere. They affect atmospheric dynamics and weather patterns. As the atmosphere is a layered one with higher density below and lower density above, it forms a stable stratified system. In this stable stratified system, internal gravity waves occur between troposphere and stratosphere. The breaking of internal gravity waves can lead to generation of turbulence, which contributes to mixing and affects the weather patterns. Similarly, in ocean where stratification of the water exists with high density water below the low density water, the internal gravity waves can occur in the ocean's interior. The interaction of internal gravity waves enhance mixing of nutrients and gas in the ocean and leads to biological productivity and ecosystems. These waves are also useful in providing information about thermocline structures and vertical heat transport in oceans. Finally, in the Earth's core, where the fluid is liquid iron, internal gravity waves are generated. These internal gravity waves are influencers of the geomagnetic field dynamics. The geomagnetic field fluctuations, which can be observed as secular variations on the surface, are somewhat affected by the internal gravity waves. The internal gravity waves also affect the propagation of P waves, which propagate through the Earth's outer core fluid. In conclusion, we can say that internal gravity waves are a fundamental type of waves which are very much prevalent in various natural phenomena related to geophysical applications. They are very much important for Earth's dynamic processes, which are time dependent and are interconnected. It is important to note that internal gravity waves are periodic oscillations within stratified fluids in the interior, and for internal gravity waves, the necessary ingredients are gravity, stratification, and volume of fluid. The restoring force is the buoyancy force. Finally, the internal gravity waves play a crucial role in various geophysical processes by influencing energy transfer, mixing, turbulence, and large-scale dynamics within various geophysical fluid applications. One can look into the following references for more information and applications of the internal gravity waves. Thank you.